All right, everybody. Let's go ahead and get started. So thank you for everybody that has mentioned to me about ELC. I've noticed when I logged in that it's listed as inactive for that class for some reason. I sent an email out to try and figure out what has changed and why. Hopefully we'll get a response back very quickly. In the meantime, I know that one or two of you have sent out the link to the GroupMe, and I've answered the emails that I've received from students. So I'm hoping that that will be disseminated out so that everybody will know where to click so that we can get everybody into class here. But we'll keep moving forward with our alkene chemistry. We left off, we were talking about hydration, right? Hydration was the addition of what across an alkene? Water. So we get hydrogen on one side, we get OH on the other side. And then we said, well, what if we swapped out water for an alcohol? Previously with hydration, we were going from an alkene to an alcohol product. And we saw our enantiomer that may be possible if we create a chiral center. And that's really one of the layers of complexity. If we replaced that water with alcohol, then instead of making an alcohol, we were instead making what? Was an ether, right? Depending on what the R component was, we could have a methyl ether, an ethyl, an isopropyl, really anything that we could imagine would work out. But the mechanism was almost identical. I don't want to say identical because there are differences, right? But almost identical. The difference being what we've seen here, that what's highlighted R for H. Then everything else works the same as it did. Okay? So let's move forward. The intermediate for the hydration and the addition of the alcohol across, what was the intermediate that we created? What type of intermediate? When we added that hydrogen, what did we create? Carbocation, exactly, right? So we made a carbocation. So that's going to be the intermediate for a number of our reactions. It's not going to be the intermediate for everything. But when we create that carbocation, right, we're acidic conditions, we're protonating using the pi electrons of the alkene to reach out and grab that electrophilic hydrogen. We form the carbocation, then the nucleophile comes in and attacks. And the nucleophile could be an anion when we're talking about something like a bromide or a chloride. It could be a neutral water or a neutral alcohol when we're looking at our hydration reaction and the variation on that, right? So we have that possibility as well. So we've got to think about, thank you, Dr. Morrison. So we've got to think about what's happening here. Oh, no, we're not updating anything. So we're always going to be mindful of the starting functional group, what we're converting it into, alkene to alcohol, so on and so forth. And we're also going to be thinking about the intermediate that is formed and what the consequences of that intermediate's formation is. One of the consequences of our carbocation formation is a rearrangement possibility. And this is going to speak to part 3 of your chem draw that will be posted up this week, a little bit later in the week and due after we get back from the instructional break. We have something called a 1,2 hydride shift, and I've mentioned that to you before. That's the shifting or moving of a hydrogen from one position to the next. We call it a hydride because it is a negatively charged hydrogen. It has 2 electrons, which normally a hydrogen, certainly a proton, would have no electrons, right? So let's look at, oh, I'm in green here. Let's go to blue. Let's look at our starting material. Okay, so here's our starting material. And I'm going to show you Hbr addition, right? So we know how this one works. First step of the reaction is drawing the arrow from the middle of our alkene to the hydrogen, then breaking the hydrogen-bromine bond. No surprise there. Will this lead to a regio-specific intermediate? Absolutely, right? Following Markovnikov's rule, we're going to form the most stable intermediate that we can, which is we've got the possibility of forming a primary carbocation or a secondary. The secondary is going to be preferred. Okay, so we draw that out and we say there is our secondary carbocation. Now, traditional product would be the result of the bromide then coming in and attacking like so. And that would give us a total of how many products? 1, 2, 3, 4, 5. How many chiral centers do we have on this compound as a result of this reaction? We're forming 1, right? And that would be right here. The bromide could attack from the top or from the bottom. Now, again, just to clear up any confusion, your textbook does not start talking about stereochemistry until the latter stages of the chapter. Personally, and I know my colleagues agree that talking about stereochemistry from the beginning means that you don't have to relearn. You don't have to kind of think of things in 2 different ways. So we're just going to, we'll look through and see our stereospecificity or our lack of stereospecificity in our products from the beginning. All right, so I've got all this white space. Let's do a rearrangement, right? What does a rearrangement look like? This is something that costs energy. It's not done for free. Shifting a hydride, shifting a hydrogen with its electrons over is not done for free. So we have to put energy into the system, but we get paid a dividend, right? There's a benefit from this happening. We absorb energy, we shift, we move, and we're going to end up getting something out of it. So if I look to an adjacent carbon, I could look to the right, I could look to the left. But what's happening is we're moving a hydrogen, which is going to result in the formation of a carbocation on the carbon that was holding that hydrogen. So if I look to the right, that's just going to give me a primary carbocation. We already avoided that in our initial protonation. So that's not going to happen. But this one, if I shift this over, and let's do it just like that, right? So I'm indicating, I'm drawing it straight from the middle of that bond, that carbon-hydrogen bond. What type of carbocation am I making now?
A tertiary.
A tertiary, exactly, right? So I do my hydride shift. And there's my tertiary. Well, let me see here. So the driving force behind this is I form a more stable intermediate. We're not going to do this if it forms a less stable. That's just not going to work for us. We're not going to absorb, we're not going to pay molecular energy in order to get a least stable or less stable intermediate. So now our bromide comes in. And it attacks. And how many products do I get out of this rearrangement? It's a carbocation, it's trigonal planar, but in this instance, I happen to have a carbon tertiary carbocation that has 2 methyl groups coming off of it, so it is not chiral. So we have not created a chiral compound. So instead of multiple products, we're just going to get the 1. And I have to specify that it's a hydride shift because we also have something called a 1,2 alkyl shift, where we could shift over an alkyl group, a methyl and ethyl. In fact, we'll find that we could actually do a ring expansion. We could move up, we could break a ring and expand it, which would have a beneficial result, essentially. All right. So a lot of possible products here. We've got the conventional substitution reaction or addition reaction, and then we've got our shift, our rearrangement. Let's look at a 1,2 alkyl shift. See how similar it is. Okay, so HCl in this case. We know how our mechanism works for that first step, the acquisition of that hydrogen. The same answer that we asked before. Which carbocation are we going to create? Well, the secondary, because that is the more stable of the 2 versus the primary. If I had my chloride come in and attack just like so. Actually, what I'll do it like this. And then we're going to create two products just like we did before. We're creating a very similar set of products here. We just have one additional carbon, one additional methyl group on this starting material. However, I could also take that secondary carbocation and I could shift this methyl group over in the same fashion that I did the hydride. So I'm breaking that carbon-carbon bond. That carbon is moving over with 2 electrons, so it's going to be negatively charged. All right, there's our alkyl shift. Okay, how does that look to us? Now we've got our tertiary carbocation, but what am I missing? What did I not draw in? The methyl group, right? So previously we shifted a hydride, so there's nothing to see, right? We're not drawing in the hydrogen because it is implied. But now I've got to make sure, now we've got the bow tie. So now we've got that methyl group pointed down at the adjacent position. So we've actually changed the carbon skeleton, or really not the carbon skeleton, we've changed the positioning of the substituents on the carbon skeleton. And then, whoops. Now, be aware, I have a bad tendency to change chlorines into bromines regularly. For some reason I like bromine better, don't know why. So just call me out whenever you see me doing that. And then we're just going to attack just like we did before. And again, the issue at hand, I guess I'll keep this green, is that we're not creating a chiral center. So we don't end up with a pair of enantiomers.
Dr. Hubbard.
Yes.
Would we say that, like, are intermediates always going to do this when possible because it makes it stable, or is there only certain scenarios where this is going to happen?
So this is a situation where we would indicate in some way that a rearrangement had occurred. Otherwise, we're going to be looking behind every door for a rearrangement, right? It is a possibility, and if we add heat, if we significantly increase the heat, that's paying in energy, which allows for these rearrangements to occur. But there will be some indication, right, that it's possible, essentially, right? If we say all possible products, all rearrangement and addition products, then you know that the shifts are possible. Now, if a shift occurs that does not result in a more stable intermediate, that is going to be disfavored, right? That isn't something that we want to pay molecular money for, because it wouldn't give us the value that we're looking for, right? We want, think of it as a stock trade, right? You put in money in Apple in 1980, wouldn't that be nice? And then now you reap the benefits and we're all living on a mountaintop in Italy somewhere, right? So the idea here is that we're paying in our money so that we'll have a bigger payoff when we have a more stable intermediate. Okay. So when I look at, let me ask a question that I asked on Friday. When I'm looking at this pair, what is the relationship between those two? They are
enantiomers.
Stereoisomers, and more specifically enantiomers, right? That is the type of stereoisomer. Now, how would I describe this product mixture as a result of this reaction? I think I heard racemic mixture. So a 50-50 mix, we could make both of them with equal facility. Now, is this product mixture optically active? And we would say no, right? Because it's a 50-50 mix. So we've got the R rotating in one direction to a certain degree. The S immediately counteracts that at 50%. So that would be our answer to our optical activity. This would be optically inactive, this pairing. And the same would go for our previous up here, right? So we're tying back in concepts that we've talked about before conceptually optical activity. What is the relationship, stereoisomers, specifically enantiomers, so on and so forth. We're going to have opportunities. We certainly could make diastereomers. That would be an easy thing to do, so we need to bear that in mind. All right, so we're leveling up. Now let's go one level more. Let's do a ring expansion. This is a variation on an alkyl shift. Let me bring some of these down a little bit. Come on. All right, technology is saying no today, so we're just going to let that go. All right, so a ring expansion. We'll look at something like this. And we'll do HBr. And we'll ask ourselves, what is the product going to be from this reaction? So once again, we know what happens when we have HX. We want this to be rote, something that just your gut instinct tells you exactly how you got to draw these arrows in. Now that's going to form what type of intermediate? We mentioned this before. A carbocation, specifically a what type of carbocation?
Secondary.
Secondary carbocation, right? So we got our secondary carbocation. And so we look at this and we say to ourselves, well, do we think a hydride shift would be viable here? Well, let's investigate, right? So we'll take a look at this and we'll say, we've got a hydrogen right here. And we say to ourselves, well, if I did this, that would form this intermediate. Now, what do we think about that? At first glance, we look at it and we say, hey, that's a tertiary. So that feels right. But what else do we notice about that tertiary? What's our hybridization for our carbocation? sp2, so it wants to be 120 degrees. That's the ideal bond angles. What is it trapped in because it's part of that ring?
A 90 degree.
Exactly, exactly. So what do we have too much of for this to be stable? What do we have too much of?
Angle strain?
Say it without the question mark.
Angle strain?
Fantastic. So angle strain is what we've got too much of, right? 90 degrees, we're trying to take something that should be 120 and we're compressing it down to 190. So it gives us some bad angle strain. We don't like that. The molecule doesn't like that. So we say too much, angle strain. And that's going all the way back to chapter 3, right? Perfect. All right. The other thing that we can do, of course, would be the addition of our bromide, right? I'm not going to load up too many mechanistic arrows on here. Typically, we're only showing one path when we draw out a mechanism, so I don't want to get it too confusing. Our conventional product would be just this. This is our addition. This racemic mixture. Then we've got another option, and that is our alkyl shift that results in a ring expansion. And a ring expansion meaning that we're going to go from a four-membered ring up to a, well, let's take a look. If I were to take this bond here, well, let me just highlight this. This is very similar to an alkyl shift. Previously, for our alkyl shift, we moved a methyl group. But what if the carbon-carbon bond that you broke just happened to be part of a larger ring? Okay. So if we look at this and we say, if I break this carbon-carbon bond, what we're doing is we're breaking the bond, at this red carbon. And we're forming a new bond between the two purple carbons. So it's opening like it's on a hinge. So the red carbon is going to be electron deficient, and the two purple carbons are going to have a new bond formed between them. And then what's the size of this ring that we've expanded to? What do we think? Total of how many carbons?
5.
Five, exactly, exactly, 5. So let's go down here, or actually I'll just do it just like this. This is our ring expansion. Okay, and now I'm going to color code again. That's the same red carbon that we saw previously and the same purple carbon. So oftentimes it's a little bit jarring. You see it going from an ethyl group that is a substituent down to a methyl, but that's because we've shifted that carbon-carbon bond over by one position. So now all of a sudden we've got a secondary carbocation, and we said, no, wait a minute, that's a lateral move. We went from secondary to secondary. You just told me that there has to be a dividend, there has to be a benefit. What is the benefit in this case? What type of strain have we lost as a result of this shift?
You lost that 90-degree angle strain.
Exactly, we lost the angle strain, right? We went from 90 degrees. Now, what's our planar cyclopentane? We said that is 108 in its planar form, and of course it can pucker a little bit. That's not right at 120, but it's certainly a lot closer, so that'll be nicer. So the strain that we lost wasn't in the stability of the carbocation. We lost strain due to the angle compression. So that's why our ring expansion can help us out here. So then, now all of a sudden we've got another layer to the onion. Okay, so if we said our bromide has been patiently waiting for this to occur, it attacks. How many products can we form here? How many chiral carbons are we creating with this product? Let's draw out the product just in a general sense. The product is going to look like this, wouldn't we say? How many chiral centers? We've got 2 all of a sudden, right? So now we've got 2. Previously, we just had 1. So if we've got 2 chiral centers, the likelihood, the max number of stereoisomers is 2 to the n, which gives us a total of 4, right? Our n is 2 because that's the number of chiral compounds or chiral carbons. So what means what I've got to do is I've got to go through all my possibilities. I said, well, what if bromine was a wedge and methyl was a wedge? Okay, and the methyl, of course, that we're looking at right here, the chirality of that methyl happens when the ring opens up and when the 2 purple carbons form their new bond, whether that methyl will be pointed down or whether it'll be pointed up. Equally possible with both. We could also have dashed. Then we could have wedge and dashed. Or dashed and wedged. So this is just going through all the possible combinations. So that has some consequences, obviously. Okay. Hydride shift, alkyl shift, could be methyl, ethyl, any number of alkyl groups, ring expansion, all of which resulting in some type of strain reduction, which is what makes it viable.
Dr. Hubbard,
Uh-huh.
How would you go about naming this last product here?
The ones in green that we've got.
Hmm.
So that would be a 1-bromo-2-methyl cyclopentane, and then you would just have to put in your RR, your SS, your RS, and your SR. So you just have all 4 variations.
Okay, so if you were to like choose one over the others, it wouldn't be wrong.
What do you mean now?
Like if I were to name the first one, I wouldn't be counted off if I like didn't include the other stereochemistry.
You would. Every name would have to have the stereochemistry specific to the structure you were shown.
Okay, thank you.
Right. So if you were asked in general, so if I said what's the general name without stereochemistry included, it would just be a 1-bromo-2-methyl cyclopentane. Stereospecific, I'd have 4 different names, their variation only in that first parentheses that gave us the stereochemistry. Does that make sense?
Yeah, thank you.
Excellent. All right, so let's talk about halogens to alkenes. You've done this in lab. This was your diphenylacetylene from last week, right? So we're going to look at alkenes adding bromine in this instance. We'll start out with bromine. We'll start out with cyclopentene. There's Br2. Br2 is the electrophile. Our alkene is our nucleophile. Our isolated alkenes are going to be our nucleophilic in nature, those pi electrons. Now, I'm going to draw this next part out. This is for pedagogical reasons, right? This is not actually what happens in the reaction, but it's synced up a little bit better with what we've just been looking at. So we're going to look at this in comparison to HX addition, and then we're going to talk about why it doesn't actually happen this way. Okay, that's a confusing statement, but let's move forward. So if I do this, right, that would seem to mesh with what we just saw with our arrows, right? We attack one of the bromines, we break the bromine-bromine bond, it forms a bromide, and that bromide then comes in and attacks. Okay, and that's bromine added to each one of the carbons. That's a 1,2 dibromination. But then I've got written here, not a detailed enough explanation. Because what am I not showing in my product? I'm not showing any stereospecificity whatsoever. I've just drawn, these are both chiral carbons, right? There is chirality there, and there is the possibility of meso because we've added the same thing to each side. So we do have to think about our meso. But we know that a planar carbocation, if that's the route that we go, should give us a mixture of dashed and wedged. Okay, so planar carbocation intermediate should give us a mixture of stereoisomers. And we say that is not what results from this reaction. Okay, we say trans is the only product formed. And what I mean by that, of course, is this. Right, so this is the only product formed as a result of this reaction. So if we were to go through a carbocation, this couldn't be the only product formed, right? Because if the first bromine added was on a wedge, and then we've truly got a carbocation, then that bromide could form a wedge or it could form a dash. There should be an equal distribution possible. Where we say, nope, that's not what we find. When we look at the debris after the reaction, we look at the product, we say, this is all we get. So there has to be a reason for that. And that means, whoops, that there is another intermediate. So this is a new intermediate for us. All right. We call this anti-addition, meaning that one of our components, one of our bromines, adds to one face while the other adds to the opposite face. They add anti to one another, and we end up with anti-stereochemistry. So bromine adds to opposite faces of the molecule. So if I started out, again, we'll look at cyclohexene and we say Br2. What did you use instead of Br2 for your lab?
pH, PB.
Okay, so pyridinium hydrobromide per bromide, safer than liquid bromine. Not by a lot, but liquid bromine is a caustic liquid that is very toxic. So we used a safer alternative, but it performs the same function, the same role. Okay, so this is syn addition, and this is anti-addition. We've used syn and anti before, right? Syn meaning on the same plane. So we see the two wedges coming up and we say, nope, this isn't going to work out for us with our syn addition. How many possibilities do we have for anti-addition? We've got 2. Are these 2 anti-additions? Can they be superimposed? Are they the same compound? So the 2 products that I've shown you 2 products. Are they the same? Can they be superimposed? What do we think? I can see people mentally flipping them in their heads, right? So this is the skill set that we get better and better at as the semester goes on. These are different and distinct compounds, right? So we do have to remind ourselves that we can form this intermediate that we're about to see, the bromonium ion, on the top face, and that results in one product. You can also form the bromonium on the bottom face. Because remember, this alkene is trigonal planar, it's flat, which means the bromine can approach from the bottom or it can approach from the top with equal facility, okay? One of the biggest issues that comes up with a lot of our alkene chemistry is that people will have one product, but they'll have left 3 other products off. So they've got a basic understanding of how the reaction occurs, but not a complete understanding of the regiochemistry and the stereochemistry that is so important. So we got to make sure that we've got full understanding. Did I hear somebody?
Yes, Dr. Hubbard.
Uh-huh.
So how are we going to know if it's a syn addition or we're dealing with an anti-addition?
You only get anti-addition. Syn addition for this reaction does not occur.
Is it that it's just too unstable?
Well, we're about to look at the mechanism, and that will answer our questions. So if we look at this, let's look at how the intermediate is formed, right? Because his question is legitimate. Wait a minute, why does it go trans instead of syn? Why can't I expect some combination of the 2? And it has to do with the fact that we're not going to go through a carbocation. So we want to make sure we don't ever make that mistake of drawing the carbocation. Let's draw this bromonium ion formation. Okay, so we're attacking one of our bromines. We're breaking the bromine-bromine bond, and then we're also using one of the lone pairs from our electrophilic bromine to attack the other carbon position that would have been a carbocation. Okay? And actually, I'm going to draw this a little bit differently. Let's draw it both coming from the top face. So we're giving it an implication of, hey, we're settling in on the top here. So we're forming what's called the bromonium ion. And let's draw this. So we went from remember the way that I've drawn this alkene, it's not actually, the hydrogens aren't pointing up and pointing down. Remember, they're pointing back and 2 of them are pointing towards you. So it's flat, perpendicular to the plane of the projector. So we're coming in from the top with our bromine, right? The top of the alkene. So that's where this bromonium ion ends up settling. Now remember that with a trigonal planar system, The hydrogens on the original alkene were all in the same plane. When the bromonium comes in from the top, those hydrogens then shift down and away. Because what's the hybridization of these new carbons in the bromonium? They're not sp2 hybridized anymore. Now they are sp3 hybridized. So they want tetrahedral symmetry. That's going to be tough given the fact that we've got this sitting on top of them, right? We've got this 3-membered ring. So we can imagine, one, we've got a bromine that has a positive charge, doesn't like it. We've got a 3-membered ring. Nobody likes that. It's going to react almost immediately. Now, what is the electrophilic part of this intermediate? It's going to be the carbons holding the bromine, right? Because it's pulling that electron density. Now, under normal circumstances, a carbon would lose out to a bromine, but this is a positively charged bromine. It's angry. It's deficient in electron density, so it's pulling even more aggressively. So this is a very electrophilic intermediate. So what happens now is the keyboard comes up. There's our bromide, right? That's the other part of our Br2. Can this bromide, it's going to attack one of the two electrophilic carbon positions. Can it attack from the side of the molecule with the bromonium on it? The bromonium is blocking that entire top part of the molecule, right? So what's going to happen is that bromide has to come in from the opposite side. This is where the anti-addition comes from. So instead of having an open carbocation that can approach from any direction, we've got a bromonium, right, which is sitting on the top. So the bromide comes in and attacks. Now, if it attacks the right-hand side, that's going to break this carbon-bromine bond. It's going to take that bromonium and kick it over to the left. On the top face, the new bromide that came in on the right side of the bottom face. This is our anti-addition. Our intermediate brackets. Okay, so there is our anti-addition. Okay, so bromonium is our intermediate. Let me write this out. Bromonium ion, positively charged bromine. You're going to hear me talk about ammoniums, positively charged nitrogen, oxoniums, positively charged oxygen. So we're getting the onium portion of it, bromonium, so on and so forth. All right, let's look at a line reaction, an example here. Br2 adding to this alkene. Now, do we think that Br2 addition, is it Markovnikov? Is it anti-Markovnikov, meaning the reverse of that? We're adding the exact same thing to both sides, so there is no regiospecificity. There is no regioselectivity. There's no hydrogen to one side or nucleophile to the other side. It's just bromine to one side, bromine to the other side. So in this case, how many products do I get? There's one. And here's our other one. And that would come from forming the bromonium on the top side, and the other possibility, which is equally as likely, forming the bromonium ion on the bottom side. So those are the two possibilities. And again, the point being made that oftentimes people lose out on points because they're not looking at the entire product distribution. They're getting the initial addition of bromine, but they're not showing the stereochemistry, absolute stereospecificity, trans only, and they're not showing the breadth of the number of products possible. So let's take this and let's do what we did with hydration. With hydration, we modified it by taking water out and putting an alcohol in. Let's modify this. And what we're going to do here is we're going to form something called a halohydrin, which means the addition of an OH and a halogen. So an OH and a Br, OH and a Cl. Chlorine and bromine is where we're going to see this happening. All right, so I'm going to put this in here. And what I do is I say, there's my X2. Now, if I just left it at this, I'd be adding whatever our X's are, the bromines, the chlorines, so on and so forth. But I'm adding in water or an alcohol. So we can do an alcohol modification of this as well. Right, but first we're going to focus on water. Water gives us the following product. Well, X, keep it generic. Okay, so we've added OH and our X, still anti-addition. Still anti-addition. That's because we're going to go through the same onium intermediate, chloronium or bromonium, depending on, oh dear, 9%. Battery saver quick. So we're looking at this and we say, this is a halohydrin, or a 1,2 halo alcohol. That's what our halohydrin signifies. Let's do the mechanism. And we're going to make this, we'll make this bromine for our mechanism here because we want to be specific. Trans-2-butene. Okay, we're attacking here. Now this is what we call a concerted reaction. All of these arrows happen in concert. They all happen at the same time. So we're not writing them out as one step, then another step, then another step. This all happens at one time. We're making these connections. So this is going to generate our bromonium ion on top of this structure. Positively charged bromine, that's our bromonium. Okay, now something essential to point out. What is the stereochemistry of my starting alkene? Cis trans EZ.
Trans.
This is trans, right? Notice that when I form a ring, when I form this three-membered ring, what is the relationship between the two methyl groups on that ring? Are they on the same face of the ring? They're on opposite faces of the ring. They're on opposite faces, so they're trans, right? We maintain that stereochemistry that is absolutely essential. We can't change that stereochemistry, otherwise we change the product that results from it. So we got to be very, very careful. So we say trans. Of course, this is trans as well. Okay, then in this case, we've got our water, and our water is going to do the job that our bromide did previously. Now, there is still bromide in solution, right? We broke apart this Br2. But when this is what we call a solvolysis reaction. We're doing this reaction in water. That's the solvent system. So there is so much more water that the bromide just gets pushed to the side. So the bromide never has a chance. The water comes in and attacks. And it has to do so, just like the bromide did, from the opposite side as our bromonium. So that gives us what type of addition?
Anti-addition.
Anti-addition, fantastic. Okay, so we end up with this. We say our bromine goes over to the left-hand side. Now, could I have used water to attack the left-hand carbon? Absolutely. That's perfectly fine. You could attack either carbon positions. It will still only end up giving you 2 possible products, right? You can draw out 4, but you're going to find that 2 of those are identical. Pairs of 2s are identical to one another, but sometimes it's good to do the long division like that. All right. Are we done with our mechanism? Or have I shortcutted? Probably, if I'm mentioning it.
Where'd the methyl group go?
Oh, absolutely true. Unintended shortcut. Okay. There's still a shortcut, right? I took off my hydrogen from my oxygen. Magically, it's gone, but we know that's not the case. So we look back, we get rid of that. And we say hydrogen here, hydrogen here. Okay, what am I missing now? If an oxygen attacks with a lone pair to form a new covalent bond, that means it's deficient by 1 electron, so it would be an oxonium ion, a positively charged oxygen. So we got a positive charge here, and we got to get rid of that positive charge. Now, the oxygen has a way of getting rid of the positive charge that the bromonium doesn't. The bromonium just has to grab a covalent bond. All we need to do for this oxygen is deprotonate it. And what do we have in solution that can deprotonate it? Well, this is where bromide
Water.
comes along, or water, right? So we got bromide and we've got water, both of which are basic or can be basic in an acidic environment and can deprotonate. So we say Br minus or water. Do this. Didn't do my brackets here. And that gives me my final product, or one of multiples. Okay, and that's our bromohydrin in this case. Now, replace H2O with ROH above. What we get as a result of this, the mechanism would be the same, right? Now we've got OR instead of OH, just like we did with the modification of our hydration reaction. So again, what I'll stress to you is what I mentioned in the beginning of the semester, which is we've got to make sure we're not trying to memorize and take mental snapshots of everything and just hold it in the back of our brain and say, well, we'll figure it out when we see it. There's a lot of interconnectivity between these mechanisms, things that are similar, things that if you understand a concept, you can apply it in multiple conditions, multiple situations. That will save you time, it will save you effort. It's the idea of working smarter, not harder, right? Memorizing is the hardest way to go through this. Setting these things up next to each other on your desk and saying, how are they similar, is going to help you quite a bit, writing these things out, okay? So that's the addition of our ether. So we'll keep going with that on Wednesday, okay? And we'll talk about the regiochemistry of this reaction. Have a good afternoon. We'll see you in lab.